This is question number 2 in exercise number 1.1 Relations and Functions chapter. You observe this question, what they are asking. Show that the relation R on the set of all real numbers. The relation is defined like this: R equal to order pair A comma B such that A is less than or equal to B square. This relation is neither reflexive nor symmetric nor transitive. That means we need to show that this is not reflexive, not symmetric, not transitive. This is one of the good example to understand reflexive relation, symmetric relation, transitive relation. As usual, in first problem, in every bit, we written 3 steps mainly from the question. In this problem also, I'll write those 3 steps. First point is, this relation is on what set? This relation is on set of all real numbers. They given R. This R indicates set of all real numbers. You know what are real numbers? Union of rational numbers and irrational numbers are known as real numbers. Or any number you can mark on the number line is known as a real number. And real numbers in interval form we'll write like this: open interval minus infinity to plus infinity. You take any number in between minus infinity to plus infinity, it is known as a real number. And second point is, this relation is on which set? Given that the relation R on the set of all real numbers. They given that R is a relation on set of all real numbers. That means R is a relation from real numbers to real numbers. Third point is how the relation is defined. The relation is defined like this: order pair A comma B says that A is less than or equal to B square. Here, understanding this relation is important. I'll check few examples which order pairs are there in this relation. Here, R is a relation on set of all real numbers. No? So, this A must be a real number and B must be a real number. A and B both are real numbers and A less than or equal to B square. For example, I'll take one order pair 1 comma 1. Here 1 is a real number. 1 comma 1 belongs this relation or not? The order pair 1 comma 1 belongs this relation. First point satisfied, both are real number. Second point is 1 is less than or equal to 1 square. See, 1 less than or equal to 1 square is 1, right? Now you see 1 is not less than 1. In this 1 is not less than 1 but 1 equal to 1. So if I ask this is true or false, means this is true because less than or equal, any one condition satisfied, it's okay. 1 equal to 1, that means the order pair 1 comma 1 belongs to this relation. I hope you are understanding. Now my question is, order pair 1 by 2 comma 1 by 2 belongs to this relation or not? First point, 1 by 2 is a real number, 1 by 2 is a real number. Okay. Second condition, 1 by 2 is less than or equal to 1 by 2 whole square. 1 by 2 whole square is 1 by 4. Is it true? 1 by 2 means 0.5, less than or equal to 1 by 4 means 0.25. Is it true? 0.5 is less than 0.25? No. Is 0.5 is equal to 0.25? No. So this tells you that this set of 1 by 2 comma 1 by 2, 1 by 2 is a real number, 1 by 2 is a real number, but it is not satisfying this condition. So 1 by 2 comma 1 by 2 does not belong to this relation. I hope you are understanding, right? Suppose I will take 1 comma 2. Is 1 comma 2 belongs to this relation or not? First point, 1 is a real number, 2 is a real number. Yes, correct. Now this order pair 1 comma 2 satisfying this condition, you need to check 1 less than or equal to 2 square. 2 square is 4. Is it true? Yes, 1 is less than 4. It is true. As this is true, what I can say? I can say that order pair 1 comma 2 belongs to the relation. Here, it is important that which order pairs are there in this relation. This R contains infinitely many elements, many order pairs, right? We cannot write all those order pairs here now in a roster method, right? So you need to know how to check a particular order pair belongs to that relation or not. Okay. Now I need to check this relation is reflexive relation or symmetric. No. I need to show that this relation is not reflexive. This relation is not symmetric. This relation is not transitive. How to check reflexive condition? For any x belongs to R set of all real numbers, order pair x comma x is there in the relation, then we say that relation is reflexive. Okay, for any x belongs to real number, order pair x comma x belongs to R, then we say the relation is reflexive. In this example, we need to show that this relation is not reflexive. When you are trying to say this relation is not reflexive, best thing is find an example. I'll take 1 by 2. Is 1 by 2 is a real number? Yes, 1 by 2 is a real number. Now I'll check that is 1 by 2 is less than or equal to 1 by 2 whole square. 1 by 2 whole square is 1 by 4. You observe this 1 by 2 less than or equal to 1 by 4. Is this true or false? 1 by 2 is 0.5. 1 by 4 is 0.25 less than or equal to. See, 0.5 is not less than 0.25. That condition fails. 0.5 not equal to 0.25. That condition also fails. That tells you that this is false. As this is false, I can write that 1 by 2 comma 1 by 2 does not belongs to the relation. Here, I taken one element in the set of all real numbers. I checked this order pair x comma x type that is not in the relation. That means this element fails to satisfy reflexive condition. So I can say that this relation R is not reflexive. See, in this relations and functions, when the relation is not reflexive, when the relation is not symmetric, when the relation is not transitive, writing the answer very easy. We give a counter example like this. See, so and so element fails satisfying reflexive condition. That's why this relation is not reflexive. We'll say like that very easily. But when it is reflexive, you cannot give an example like this. When it is reflexive, then you need to check for every element in that relation, in that for every element in that particular set satisfying x comma x belongs to R or not. I hope you understand. This relation is not reflexive. Now I'll check is this relation is symmetric or not. In this question, we need to show that this relation is not symmetric, right? Okay, this is the relation. We need to show that this relation is not symmetric. For that, I'll take one element x comma y in this relation. I'll take one element x comma y in the relation and I'll try to prove that y comma x does not belongs to the relation. Okay, so let me take one order pair in the relation. I'll take 1 comma 2 in the relation. Now you need to check 1 comma 2 is there in the relation or not. Here 1 is a real number, 2 is a real number. Okay, is this order pair satisfying this condition or not? 1 is less than or equal to 2 square. 2 square is 4. Is this true or false? Here 1 is less than 4. Yes, 1 is less than 4. This is true. That means the order pair 1 comma 2 belongs to relation. Now what I need to check? I need to check 2 comma 1 is there in the relation or not. I need to check this. When I'll say 2 comma 1 is there in this relation, if 2 is less than or equal to 1 square, that means 2 is less than or equal to 1. You check, is it true? Is 2 is less than 1? No. Is 2 equal to 1? No. So what happened here? 2 is less than or equal to 1 square. This is false. Is this true? Means it is false. As it is false, what I can say? I can say that the order pair 2 comma 1 does not belongs to the relation. Here there exists 1 comma 2 in the relation, but 2 comma 1 doesn't belongs to the relation. It fails. The order pair 1 comma 2 fails to satisfy symmetric condition. I can say that this relation is not symmetric. Here one important point is finding an example like this. It is not necessary you also take 1 by 2 and you prove like that. You can take one more order pair which is in the relation x comma y such that y comma x does not belongs to the relation. You can find such example. It's not compulsory you by heart this and you write the same order pair. You can find so many examples like this. So finding such type of examples is little difficult when you try the problem your own. Okay. Now transitive. In this, we need to show that this relation is not transitive. So as this relation is not transitive, I need to find a pair of order pairs x comma y belongs to R and y comma z belongs to R, and I need to prove that x comma z does not belongs to the relation. If I can find an example which is satisfying this condition, then I can easily say that this relation is not transitive. Okay. I'll take one example like this. I'll take 10 comma 4. I'll just check that then 10 comma 4 is there in this relation or not. First point, 10 is a real number, 4 is a real number. Second point, you need to check that a is less than or equal to b square. Here 4 square is 16. Is it true? 10 is less than 16. Yes, it is true. As it is true, 10 comma 4 belongs to this relation. Yes, correct. Now I am finding pair of order pairs like x comma y. Now I need to find y comma z. Y is already fixed here. Y is 4. I'll take 4 comma 2. Now I'll check this 4 comma 2 is there in the relation R or not. First point, both are real numbers. Second point, a less than or equal to b square. 2 square is 4. Is the statement is true? 4 is not less than 4, but 4 is equal to 4. Yes, equality condition is satisfying now. So this is true. Okay. So what happened? I am able to find x comma y, y comma z in the relation. Now I need to look that x comma z is there in the relation or not. What is x comma z? 10 comma 2, the order pair 10 comma 2 is there in the relation or not, that I need to check. Okay, order pair 10 comma 2, 10 is a real number, 2 is a real number. Now is this satisfies that condition a less than or equal to b square? 10 less than or equal to 2 square, 2 square is 4. Is it true? 10 is less than 4? No. Is 10 equal to 4? No. So from that we can easily say that 10 comma 2 does not belongs to the relation. Yes, from this we can say that 10 comma 2 does not belongs to relation because it fails to satisfy that condition a less than or equal to b square, right? So what happened? I am able to find x comma y, y comma z in the relation such that x comma z is not in the relation. So I can write from this the relation R is not transitive. Therefore, this relation is not reflexive, not symmetric, not transitive. I'll name these things. This is 1, not reflexive. This is 2, not symmetric. This is 3, not transitive. From 1 to 3, I can say that R is neither reflexive, nor symmetric, nor transitive. I hope you understand this solution. You observe this question number 3. This is easy question compared to last question. Check whether the relation R on this set. The relation is defined like this. We need to check this relation is reflexive or symmetric or transitive. We need to check these things. As usual, what we are doing in question number 1, question number 2, those 3 steps we'll write first. First step, this relation is on which set? You see here, they given set, they didn't name this set. We'll name the set. I'll name it as A. The set A is 1, 2, 3, 4, 5, 6. Okay. And second point is relation is on which set? Relation R is on this set. That means R is a relation on A. This is second step. Third step, how the relation is defined. The relation is defined like this. It is a ordered pair A comma B such that B equal to A plus 1. Here you need to understand few things. Which order pair is there in the relation R? As R is a relation on A, this element A must belongs to set A, this element B also must belongs to set A, and this order pair must satisfy this condition B equal to A plus 1. So I'll write this relation in roster method so that we can easily identify this relation is reflexive or symmetric or transitive. As A must belongs to set A, I'll take 1 in place of A. Okay. For A equal to 1, you put A equal to 1 here, what you will get? B is 2, right? So the order pair 1 comma 2 belongs this relation. First point is 1, 2 both are there in this set, and this order pair 1 comma 2, when I substitute in this, it will satisfy. In place of A you write 1, in place of B you write 2. You see here it satisfies. Now I'll write the next order pair. Here first element will be from set A, 1 is already over here, so I'll take A as 2. If I take A as 2, put A 2 here, what you will get? B is 2 plus 1, right? So B is 3. So order pair 2 comma 3. 2 is there in this set and 3 is also there in this set, and the order pair 2 comma 3 satisfies this condition. Now I'll write the third order pair. As A is there in set A As 1, 2 already completed, I'll take 3. Put A 3 here, B is 4. So the order pair 3, comma 4 belongs to relation. Similarly, put A is 4. When you put A is 4, B is 5. Put A is 5. When A is 5, B is 6. We can take A is 6 also. If you take A is 6, put A is 6 here. 6 plus 1 is 7. You will get B is 7 when you put A is 6. But A, B both must belong to this relation. As 7 is not in this relation, the order pair 6, comma 7 does not belong to this relation. I hope you are understanding. In place of A, if I take 6, B will become 7. So 6, comma 7 does not belong to this relation. So finally, I written given relation in roster method. Actually, this is in set builder method. Now we written it into roster method. Now it is easy for us to check reflexive, symmetric, transitive. How to check reflexive condition? For any x belongs to set A implies order pair x comma x belongs to relation, then we say that relation is reflexive relation. Here, I'll take one element from set A. Suppose 1 is there in set A. Yes, 1 is there in set A. Order pair 1 comma 1 is there in this relation? No. Here, we can conclude that the relation is not reflexive. For 1 belongs to set A implies order pair 1 comma 1 does not belong to relation. Therefore, I can say that the relation R is not reflexive. Now I'll check symmetric condition. What is symmetric condition? For every order pair x comma y in the relation, if y comma x also present in the relation, in that case we say that the relation is symmetric. Here this is the relation. Here 1 comma 2 is there in the relation. For 1 comma 2, 2 comma 1 is there in this relation? No. So here we can conclude that this relation is not symmetric. For 1 comma 2 is there in the relation. For 1 comma 2, 2 comma 1 does not belongs to relation. So I can say that this relation R is not symmetric. So this relation is not reflexive, not symmetric. Now I'll check transitive condition. How to check transitive condition? For every pair x comma y belongs to R and y comma z belongs to R. For every such pair x comma y comma z, if x comma z is also present in the relation, then we say the relation is transitive. Now you observe here this ends with 2. You look, any other starts with 2. Yes, here this is there, it starts with 2. That means there exists x comma y comma z. Look here, x comma y comma z exists. X comma y comma z. What is x comma z? X comma z is order pair 1 comma 3. Order pair 1 comma 3 is there in this relation? No. So we can conclude here this relation is not transitive. There exists x comma y and y comma z in this relation. Now we look that x comma z, that means 1 comma 3 is there in the relation or not. You can check 1 comma 3 is not in the relation. 1 comma 3 does not belong to this relation. Therefore, the relation R is not transitive. So, given relation is neither reflexive nor symmetric nor transitive. When we are able to write given relation like this in roster form, in those cases, most of the time checking reflexive, symmetric, transitive is very easy. I hope you understand this solution. This is question number 4. You observe what they are asking in this question. Show that the relation R, which is defined on real numbers, and the relation is defined like this. This relation is reflexive, transitive, but not symmetric. We need to prove that. As usual, for all the 3 problems what we done till now in this exercise, we written 3 points in the beginning. I'll write those 3 points here. You observe they given this relation on set of all real numbers. So first I written what is given set. Given set is set of all real numbers. You know what are real numbers. Any number in between minus infinity to plus infinity are known as real numbers. Okay. And second point is the relation R in R. That means R is a relation on set of all real numbers. They mention that R is a relation on set of all real numbers. And third one is how the relation is defined. You see, the relation is defined as order pair A comma B such that A is less than or equal to B. First thing, to understand this solution very clearly, you need to know which order pair is there in this relation. As this relation is on set of all real numbers, A is a real number, B is a real number, and this order pair must satisfy this condition. For example, if I take 1 comma 2, is 1 comma 2 is there in this relation? For that, you see here 1 is a real number, 2 is a real number. You check that 1 is less than or equal to 2. Is this is true or false? Yes, 1 is less than 2. It is true. As it is true, the order pair 1 comma 2 belongs to this relation. Similarly, if I take 10 comma 4, 10 comma 4 is there in this relation or not? How to check? First point, 10 is a real number, 4 is a real number. Second point, you need to check the order pair 10 comma 4 satisfies this condition or not. 10 is less than or equal to 4. You observe, is 10 is less than 4? No, 10 is not less than 4. Is 10 is equal to 4? No, 10 is not equal to 4. So we can say that this order pair does not belongs to the relation, right? Now you know what type of order pairs are there in this relation. Now we need to show that this relation is reflexive. We need to show this relation is reflexive. When it is reflexive, you have to write the answer carefully. One main thing that many students confuses is writing the solution of every problem. Here, from problem to problem, solution will vary little bit. Here, how to write this relation is reflexive relation. What is reflexive relation? For any x in set A implies order pair x comma x belongs to relation, then we say that relation is reflexive relation. Here, in place of A, they given real numbers. So what I'll do, I'll take a real number A. I suppose A is a real number. I taken one real number A. Now, order pair A comma A belongs this relation or not? First point, A is a real number, A is a real number. When the order pair A comma A belongs this relation, if it satisfies this condition, is A is less than or equal to A? A cannot be less than A. First condition is failed. Is A equal to A? Yes, second condition is satisfying A equal to A. From that, I can say that this inequality is true. As this inequality is true, order pair A comma A belongs to the relation. I hope you are understanding. If I take any real number A, you know that A is less than or equal to A. This is true. As A is a real number and order pair A comma A satisfying this condition, from this I can write that the order pair A comma A belongs to the relation. From this I can say that the relation R is reflexive. See, some students they'll write the answer like this: 1 is a real number, 1 comma 1 belongs to relation. That's why this relation is reflexive. No, you cannot use such type of example when it is reflexive. You can give counter example when you can give counter example when it is not reflexive. So I proved that this relation is reflexive. Now I'll check symmetric. How to check symmetric condition? You see, in this, they are asking, show that it is not symmetric. When it is not symmetric, it is enough to give a counter example. Symmetric means what? For every x comma y in the relation, if y comma x also present in the relation, then we say that relation is symmetric, right? Here, they are asking us to show not symmetric. So I'll give a counter example. I'll take one order pair 1 comma 2 in the relation. Is this order pair is there in this relation? First point, 1 is a real number, 2 is a real number. And is 1 is less than or equal to 2? Is this order pair satisfying this condition? That I need to check. Is 1 is less than or equal to 2? Yes, 1 is less than 2. That means order pair 1 comma 2 belongs to this relation. From this, now I need to check that the order pair 2 comma 1 is there in the relation or not. First point, 2 is a real number, 1 is a real number. This order pair satisfying this condition, you check 2 is less than or equal to 1. Is 2 is less than 1? No. Is 2 is equal to 1? No. So this order pair 2 comma 1 does not belongs to this relation, right? So we identified that for order pair 1 comma 2 in the relation, 2 comma 1 doesn't belongs to this relation. So we can write that this relation R is not symmetric. One important point you need to keep in your mind: when it is reflexive, you cannot give example type like 1 is a real number, 1 comma 1 belongs to, like that you cannot write. When it is not reflexive, then you can give counter example. You see here, when it is not symmetric, we just given a counter example, right? If it is symmetric, then you cannot give examples like this. If it is symmetric, then you cannot give examples like this. As it is not symmetric, I given a counter example. I'll check transitivity. Is this relation is transitive or not? What is transitive relation? You take x comma y in the relation. You take x comma y and y comma z in the relation. If such order pair exists, then we look that x comma z is there in the relation or not. If x comma z is there in that relation, then we say that that relation is transitive. Okay. Now I'll take a comma b in the relation and b comma c. Such type of order pairs exists in this relation. When the order pair a comma b belongs to R, if I take an a comma b belongs to R, it indicates that a is less than or equal to b as per this relation. So as a comma b belongs to R, from this we can write a is less than or equal to b. And you see, the order pair b comma c belongs to R. From this we can write that b is less than or equal to c. Here you know that a is less than or equal to b and b is less than or equal to c. So what I can write here, I can write like this: a is less than or equal to b, b is less than or equal to c. From this, what you can conclude? You can conclude that easily a is less than or equal to c. Now the point is, I need to check a comma c is there in this relation or not. See, a is a real number, c is a real number. As a is less than or equal to c, look here, a, c, both are real numbers, and I came to know that a is less than or equal to c. So what I can say? I can say that the order pair a comma c belongs to this relation. As we got this, from this I can write that the order pair a comma c belongs to the relation. So therefore the relation R is transitive. This relation is transitive. And you observe this relation is reflexive, this relation is not symmetric, this relation is transitive. We'll name here, this is 1, this is 2, and this is 3. From 1 to 3, what we can say? We can say that R is reflexive and transitive, but not symmetric. I hope you understand solution for this question. If you like this video, please drop a like. Share this video with your friends. In case if you are not yet subscribed to this channel, subscribe now. Thanks for watching. Take care. Bye-bye.